In this video, we're going to solve this question. The problem reads, find I/O and VO in the circuit. So they give us this circuit diagram and they want us to find the current I/O, which is the current that passes through this 3K resistor, and the voltage VO, which is the voltage drop across this 6K resistor. Now, there are multiple ways we can proceed with this problem, but the way we're going to solve this problem is we're going to use nodal voltage analysis. So we should remember, when we're going to use node voltage, we should identify the essential nodes. So we have one essential node here, we have another one here, and we're going to have one big node at the bottom. I'm just going to label it right here. And we're going to take the bottom node as our reference node. We usually take the bottom node, but really, that can change, right? Now, once we have identified our essential nodes, we know we're going to be using node voltage. So we need the voltage at each of these nodes. So I'm going to call this V1, and I'm going to call this V2. Node 1, node 2. I'm also going to write the polarities for each of these voltages in reference to our node we chose for the reference node. So for example, we know the voltage at node 1, which we labeled as V1, is going to be plus to minus, which is this node down here. This is our reference node. Then for V2, we're going to have plus, minus, right? And that's the voltage at node 2 in relation to our reference or to our ground node. Now, let's start to write some equations. So the first equation we're going to write is going to be at node 1. We're going to say node voltage at node 1. Now we should remember, when we're performing node voltage, we're going to treat it as Kircchoffs current law, but we're just going to assume that the current is going to be leaving the node. So when we look at this, we have a current going this way, and this way. And that may not be true, but when we write our node voltage equations, we're just going to assume that. Alright, so when we look at this now, we know we have a 2 milliamp current source that's actually going to be flowing in this direction here. But because we're going to assume is actually leaving the nodes and not entering the nodes, we're going to write this as a negative current. So the current in this part of the circuit is going to be negative 2 milliamps. So I'm just going to write it as times 10 to the negative 3. I'll put that in brackets. Plus, we have a current that's going to be leaving this node here, right? We know that current is going to be I/O. We know the current is going to be I/O. So let's write I/O. Plus, we have the current going in this direction here. But because this current that's going to leave this node is going to go straight ahead this way and then enter this node here, we're going to take the difference of these two voltages divided by this resistor. So we have V1 minus V2 over 6,000. And all of that equals 0. Now before we continue, I want to point something out to you, right? Anytime we're doing the node voltage method, if we have an unknown current, we always want to write that unknown current in terms of voltage over resistance. So for example, I/O, we're going to write it as V1 over 3,000 because we know the voltage V1 at this node is the same voltage across this resistor here. So instead of I/O, we're actually going to write it as negative 2 times 10 to the negative 3 plus V1 over 3,000 plus V1 minus V2 over 6,000 equals 0. Now what is the LCD? Now out of these three terms, what is the LCD? Well, we know the LCD is going to be 6,000, right? So we can multiply each term by 6,000. Now let's start to simplify this. We know 6,000 times negative 2 times 10 to the negative 3 is going to give us negative 12 plus, 3,000 is going to go into 3,000 one time. 3,000 can go into 6,000 two times. So we're left with 2 V1 plus, these two are going to cancel out. So we have V1 minus V2 equals 0. So when we simplify this now, we're going to get 3V1 minus V2 equals 12. So this is our first node voltage equation. Now let's write a node voltage at node 2. So let's do that. We have node voltage at node 2. Now we know we're going to assume that the current is leaving this particular node. So we're going to assume the current is going this way now, right? So we're going to write this as the difference between V2 and V1 over 6,000. V2 minus V1 over 6,000. Then the current in this node, we're going to assume it's leaving, and we actually have a current source that's actually following what we are going to assume. Therefore, this is going to be a positive current of 4 milliamps. So we have plus 4 times 10 to the negative 3. Plus, we have, and our last current is going to go this way. So we're just going to write this current as a relationship between the voltage and the resistance. So because we know the voltage V2 is here, which is the voltage at this node, and we know this source and this resistor are in parallel, the voltage here is going to be the same voltage that is here. Therefore, we know to write the current in this particular leg here, we're just going to write it as V2 divided by 12,000. So we have V2 divided by 12,000. And all of that equals 0. Now when you look at this, we can just start to simplify this. The LTD is going to be 12,000. Which means if we was to simplify this using the LTD of 12,000, this is going to be 2 V2 minus V1 plus we have 12,000 4 times 10 to the negative 3 plus we know 12,000 is going to cancel out with this, so we're going to be left with V2 equals 0. Now when we simplify this now, we're going to get 2V2 minus 2V1 plus 48 plus V2 equals 0. Therefore, negative 2V1 plus 3V2 equals negative 48. Okay, so now we have two equations, right? And this is our second node voltage equation. Now that we have this, we're pretty much good to go. We can either use simultaneous equations or we can use the matrix method. So for me, I'm always going to use the matrix method. I think it's easier, it's more foolproof, and once you enter everything in correctly, you will always get the answer correct. So for the matrix method, I know we're going to have, let me change the color. We're going to have 3 and negative 1. I'm going to do it right here, actually. I'll do it right here. So we have 3 and negative 1. 3, negative 1. We know what we're trying to find is V1, V2 equals, we have 12. Now that's the first equation. Now the second equation, we're going to have negative 2 for V1. And we have positive 3 for V2. And negative 48. So we're going to take the inverse of the first and multiply it by the second. So when you put this in your calculator now, you're going to get V1 equals negative 12 over 7 volts. And V2 equals negative 120 divided by 7 volts. Now let's go back up and look to see what they wanted us to find. I'm just going to circle this. Now they wanted us to find, they want us to find the current IO. And we know the current IO is going to be the current flowing through this resistor here. So because we know the voltage at this node, and we should know the voltage at this node is the same voltage to this 3K resistor, to find IO, we're just going to use Ohm's law. So we're going to say IO equals V over R. We know we're going to take the voltage at node 1, so that's V1, over the resistance, which is 3000. We know V1, we just found, was negative 12 over 7. So we can write this as negative 12 over 7 divided by 3000. When you put that in your calculator, IO equals negative 0.57 milliamps. So this is the value for the current IO flowing through the 3K resistor. Of course, I rounded this number a little bit, but really we got negative 1 over 1750 amps. Okay, so that's what we got. Now, when we solve this, they also want us to find VO, which is the voltage across this resistor here. So to find the voltage VO, we know that's just going to be the voltage difference at these two nodes. So VO equals V1 minus V2. VO equals, we know V1 is negative 12 over 7 minus V2, negative 120 divided by 7. When you solve for this now, VO equals 108 over 7, but as a decimal, that's going to be 15.43 volts. So this is going to be our answer for the voltage VO. And this is how you solve these types of problems using node analysis. Once we found the voltage at each of these nodes, we were then able to find everything else in this circuit. And remember, the reason why we know that we were subtracting was because according to the polarities, the current is going to be flowing in this direction here. So that's how we knew to subtract V1 from V2 because of the polarities. Alright, so once we found the voltages at each of these nodes, we pretty much were able to solve anything else we wanted in this particular circuit. Stay tuned for more problems.